we have a population of rabbits oscillates 18 above and below average during the year, hitting the lowest value in January, t equals 0. So January is counting at 0. February would be 1, and so on. The average population starts at 800 rabbits and increases by 6% each month. Ooh, that's different. Find an equation. All right, so we have this oscillates 18 above and 18 below. So right there, they're talking about, so oscillates means I have a trig function, a periodic function. And periodic function could be a sine or a cosine. And generally I decide to choose the sine or the cosine depending on how it starts. Does it start at its mid-level? Does it start at a high or a low? And here they're telling us it hits the lowest value in January. So we're starting at a low. Now cosine starts at a high. So if we flip the cosine, that'll start at a low. So oscillates tells me it's a sine or a cosine. The lowest value at t equals 0 tells me to use cosine. So I am going to have a negative cosine in here. 18 above and below, so then they're telling me the amplitude. Right? Amplitude tells us how far above the midline and below the midline. Amplitude. So I'm going to have 18, negative 18 times the cosine. Let's see, during a year tells me the period. 1 year. But they want me to measure time in months. Okay, so the period is 12 months. And we know that the period is equal to 2 pi over b, where b is the multiple in here. So that tells me 12 equals 2 pi over b. Multiply the b up, divide the 12 down. So b should be pi over 6. So I got b now. I've got a. I have a negative cosine. Next interesting part is this average population. Starts at 800. So normally with a cosine, we oscillate about a fixed average, right? A straight line. But they're saying that average increases by 6% each month. So what does that mean? Right here. So think back to your previous math class. If you have a population that increases by a fixed percentage, then you're going to end up with an exponential equation. So each month, so t is my months here. So that is back to a formula that looks like this. The starting amount times 1 plus r to the power t is like the compound interest formula, and 6% is our interest. So that right there, our average, that's our midline. So instead of having a steady midline, we have an increasing midline, and that increasing midline is an exponential function right there. Okay, so again, normally, let's get the line tool, we have a steady midline like that, and then the wave, oops. And then the wave oscillates around it. Here, they're saying the average, the midline, is this exponential function. Exponential functions, let's do that in red, look more like this if it's an increasing function. And so our wave's going to have to oscillate around that. Something like that, a little messy, but so that's the tricky part here. So how do we apply that? Well, normally the midline y equals k, we just add that on, right? So a function like this would be something like a cosine of bt, say we have no phase shift, plus k. K again is our average, our midline. This is going to be our new average right there. And the values they give me is starting at 800, add 6% to the power t. So we have, putting that all together, we've got our A is negative 18. We chose cosine to start off at the minimum because of the negative. We found B was pi over 6. And then K, according to this new kind of average, is 800 times 1.06 to the power t. Oops, I forgot my t over here. Cosine of pi over 6t. So this gives us the oscillation. This gives us the new average right there. Let's graph it, see what it looks like, see if this seems like a reasonable situation. Do we end up with a cosine function oscillating around that new midline? So I'm going to do two things. I'm going to graph the function I think it is. I'm also going to graph the midline like I usually do with just a straight line. All right, so let's see, population of rabbits, we'll call it P, and we got to use X here, equals the oscillating part, negative 18, cosine pi over 6, X. So there's my oscillating part. And then I want to add on the new exponential midline, 800 times times 1.06 raised to the power x. All right, so think about that with my graph back here. This graph right here is going to start us off at 800 and then increase 6% per month from there. And it's going to oscillate 18 above and 18 below as it moves up. So thinking about the range and the domain for this, let's look at a couple of years. So adjust, don't need to start at negative. We'll start off at 0, January. And let's go for 2 years. Now let's go for 3 years, 36 months. And then the lowest it's going to get is 18 below 800. So that's like, let's start at like, I don't know, 750 maybe. And then go up to, it's going to increase the 18 plus the exponential part. So let's just guess, we'll go to maybe 1,000, see what that looks like. And interesting. Thought I would see it there. Got to go higher. 6% increase per month is more than I thought. So let's go to 2,000 or 3,000. Whoa. Interesting. All right, I can see a little bit of a wave there, barely. Let's graph just the exponential part. So we'll just call that y equals 800 times 1.06 raised to the power x. Okay, why am I not seeing that? Zoom out. Wrong way. Oh, I did 100. That's the problem. 800. Okay, yeah, so it is oscillating. It's hitting at different points. To zoom back in to see it. So you can see it's below here, the purple curve, and then it's above there. Oops, make the purple more prominent. Didn't really make it more prominent. Yeah, so again, think about it. We're up around 1,800, 1,600 here, or sorry, 800 and 1,600, and we're only moving 18 above and below that. So that's not really a lot of oscillations, 18 compared to 800. And given that this is exponential, it's really going to be hard to zoom on that and see it better. That's about the best view we're going to get of it. Yeah. Yeah, so that's that vertical distance of 18 from 800 there. I think that looks pretty good. So a big difference here is instead of oscillating around a midline, trig functions can oscillate around other things like an exponential function or anything else. So let's type it in, see how we did. 18 times the cosine of pi over 6 x, nope, they want a t. Thank you for the warning. And then plus our new midline, 800 times the exponential, 1.06 raised to the power x, no t. Thank you for the warning. The previous problem is similar to this one. This one right here, we're increasing from 750 at a constant amount, so that one's going to be oscillating around a line. So just to see something similar, suppose instead of the 6%, we were increasing by, say, 100 rabbits per year. So instead of an exponential function, it would be a linear function with a constant slope. And this one we can actually zoom out on and see the oscillation a little better around that line. Oops, let's get the line here. So similar example, but oscillating around a line. Oh, we're not going to get to see it because of the 800. All right, let's make it 80 and 10, then we can see the oscillation better compared to the 18. And change the scale. Let's just do a reset on the scale. Let's see, home I think does that. And then I can zoom. And I still have to adjust the Y. So starting at 80, going by 10. So let's go up to like 200. You should see that a little better, maybe 400. That's cute. Yeah, so here we can see the oscillation around the line. The exponential makes it harder to see the oscillation because it increases so fast. So a trig function, we started off looking at them again, oscillating about a horizontal line, but they could oscillate about a slanted line. They could oscillate around an exponential function. They could oscillate around a quadratic. So we have all kinds of different options. All right.